All right, we're going to look at 6.4 on logarithms and logarithmic functions. Our objectives today will be to evaluate logarithmic expressions and to be able to graph logarithmic functions. And so the standards that we're looking at are ASE 2 and FIF 7 that kind of deal with this, but also this kind of also leads us towards pre-calculus as well with their standards. And so let's just talk about what a logarithm is first. A logarithm is the inverse of an exponential function. So you'll see on the graph I've got an exponential here, and this exponential happens to be y equals 2 to the x, because we have 1 for x, 2 for y, and then 2 for x, 4 for y, and if we come up here we'll have 3 for x and 8 for y. And remember that if it's an inverse, remember the x's and y's switch, right? And so with that being said, if this is 1, 2, then its reflected point is at 2, 1. And if this is 2, 4, then we have 4, 2. And if this is 3, 8, then we have 8, 3. And so we see that the blue and the red are inverses of each other. And remember that the green line that goes through, our line of reflection for inverses is y equals x. And so here's the definition of a logarithm. So let b and x be positive numbers and b, of course, not equal to 1 when we deal with exponentials and logs. Logarithm of x with base b is denoted by this notation here, log base b of x, and is defined as the exponent y that makes the equation b to the y equal to x true. And so think about it this way. Log base b of x is equal to y if and only if b to the y is equal to x. Now, there are a whole bunch of variables there, so let's look at a problem that makes a little bit more sense to us. Log base 4 of 64 is equal to y. Then 4 to the y is equal to 64. Now, think about the exponential for a second. 4 to what power is 64? 3, right? And so when we come back over here, the y would also be 3 here. And so what a log does is it relates where these pieces are. And we're going to look at that in an example a few moments from now. So let's look at example 1. We want to be able to just convert this from logarithmic form to exponential form. And so if we go back and we talk about what goes where, log base b of x is equal to y, and that converts to b to the y is equal to x. And so we look at our first two examples. What goes where? The base is the base of the exponential, so the 3 will stay as the base. And the exponent is what the log is equal to, so our y here becomes the exponent, so the 2 is here. And of course, 3 squared is equal to what? The 9. So let's look at example B. Now you might be saying, wait, there's no base, there's just a fraction. Okay, the fraction's there because I've just put a fraction there so you can see how this problem works. But there's no base here, and this is a definition I want to make sure you know. That if I have log base 10 of x, we just write that as log of x. It's understood that if I don't write a base, the base is 10. And so if you look at your graphing calculators, you'll see a log button. That log is log base 10. And so if it helps you to rewrite it with the base for this problem, do it. And especially when converting from exponentials to logs and vice versa, it definitely helps in that situation. And so our 10 is our base, so that's going to be the base of the exponent. The negative 3 is the power, and 10 to the negative third power is equal to 1/1000th. And so that's what we have there, converting from logs to exponentials. Now, can we convert the other direction? Of course. And that's example 2. And so if I have b to the y is equal to x, that's going to be log base b of x is equal to y. And so make sure we know what goes where. So log the b is going to be 7. Remember that the power is not going to go here, it's what it's equal to. So log base 7 of the 343 is equal to 3, right? Because again, the answer to a log is the power of the exponential, okay? Look at example B. So log base what? What base are we going to use? This is our base, log base 100. right? Of what? Log base 100 of 10 is equal to what? This here, the 1/2, right? Because remember, the 1/2 power is the square root, so the square root of 100 is 10, right? So that's what we get here, right? So if I see a log that's equal to a fraction, I'm dealing with something that's dealing with radicals if we're thinking about the exponential, okay? All right, so example 3, evaluating logarithmic expressions. So basically, you just have to figure out what it's equal to on the other side. Now, if you know your powers, getting these answers is pretty quick. But remember, we could set this equal to the y and rewrite it as an exponential to then find what y will be. And so we're going to get 5 to the y is equal to 625. And again, this is a y, not a 4. And so 5 to what power is equal to 625? Well, we can rewrite this as 5 to the y is equal to 5 to what power of this? 4. So y is equal to 4. Which means that log base 5 of 625 is equal to what? 4. Okay? When we look at the other one, we'll do the same thing. So I'm going to have 27 to the y is equal to 9. Now, when we did this a couple sections ago, dealing with these powers, we only had to convert one. But in this case, we got to convert both. Both 27 and 9 can go to what base? 3. So 3 to the third is 27, right? And we still have our y out back. And 9 is 3 squared. Now this is power to power, so I'll have 3 to the 3y is equal to 3 squared. So the bases are now the same, so I can set the exponents equal to each other. So 3y is equal to 2, meaning that y is equal to 2/3. Meaning that log base 27 of 9 is equal to 2/3 itself. Okay, so again, if you convert these from log to exponential and then deal with our exponential powers, the answers come out pretty quickly with these. Okay, so now we're going to talk about graphing, the parent function of logarithmic functions, and so all of our key information is here for this. The key again to a log is that, remember that with exponentials, if our base is larger than 1, remember it's an exponential growth function. If the base is smaller than 1, it's an exponential decay function. And we see that also play out with logarithms because remember they're inverse functions. And so these graphs are continuous and one-to-one. And remember that because it's an inverse, what we talked about in section 1, we'll flip back over there real quick and I'll go back to that graph, right? Our domain was all real numbers, right? Well, now when we talk about a log, the range becomes all real numbers. And we had that asymptote, right? And that asymptote was the x-axis, which is y equals 0. Well, now our asymptote, and we're going to fix this little typo here, is not y equals 0, but the asymptote would be that x is equal to 0. Okay, so the other keys, the range is all real numbers because this is going to grow forever. Again, it doesn't look like it's growing very fast, but it's still going upward. And our intercept is going to be at 1, 0. Okay, and so that's what we have there. And again, if our b is between 0 and 1, it is decreasing as we go from left to right. Okay, so let's look at a couple of graphs that we need to graph here. Let's start with example A. We have f of x is equal to log base 3 of x. Now, there's a couple different ways you can attack this problem. I find that the easiest way to deal with this problem is to change it from an exponential to from a log to an exponential. And so this would be 3 to the y is equal to x, right? Because remember the x goes to the other side. And so set up your table, x's and y's, right? So if I have when x is 1, right, what power would make 3 to the y equal to 1? Well, y would be 0, right? So that's why we're at 1, 0. And then the next thing I would want is when my y is 1, right? So 3 to the first is what? 3. And then I would want when y is 2, right? And so 3 squared is what? 9. And I can continue that pattern to the left and to the right. Remember, you won't go into negatives, right? Because the y can't be the y can be negative, but the x can't be negative, right? Because the x is going to get closer and closer to 0, but it's not going to cross into the negative. So again, the y can be negative and give us negative powers like negative 1, right? And that would be 1/3, and negative 2 would give us 1/9, right? And so what we end up with, so y at 1 be there and then be there, right? And it would get closer and closer to that asymptote, but it would never touch it. And so this is the graph that we're looking at for this log. And again, if I draw the exponential 3 to the x is equal to y, we would see that it would be paralleled up here and then grow this way. Okay. Let's look at it for example B. G of x is equal to log base 1/3 of x. And so again, I would recommend rewriting this as an exponential first. So 1/3 to the y is equal to x. And so I'm going to get my table of x and y. And so again, start with y being 0. Well, if y is 0, anything to the 0 power is what? 1. Right? When y is 1, what's the x going to be? 1/3. And when y is 2, what are we going to get? We're going to get 1/9, right? And if we go to 3, we would get 1/27. Don't forget we also have negative y's, right? So when y is -1, what's the x value going to be? Well, remember that would take this and flip it, and so I'm going to get 3. And when I do -2 for the y, I'm going to get 9. And if I was to go to -3, I would get 27, right? So plotting these points, we have our 1, 0 again. When x is 1/3, the y is 1. When x is 1/9, the y is 2. And going the other way, when x is 3, we get y being -1. And when x is 9, the y is -2. And so we get this picture. Now, I chose these two examples, A and B, to show you that they're similar, right? Because if we look at our points, I still got the 1, 3, and 9, and the 1/3 and the 1/9, but the y's they're associated with are opposite, right? Because we went from having log base 3 to log base of 1/3, okay? One's an exponential growth, one's an exponential decay, and the values will relate, okay? So there are those two graphs. All right, let's look at example 5 and deal with transformations. Like we've been talking all along, transformations are the same no matter what type of function I'm dealing with. The A deals with the reflections and dilations, right? If I have a negative in front of this log, it's going to reflect it across the x-axis, right? So even if my base is larger than 1 and it should be growing from left to right, that negative in front will reflect it back over the x-axis and make it look like it's decreasing, right? Well, it would be decreasing because the A was negative. And remember, if we have a number for the A, that will be a vertical stretch of the function. For H, remember that horizontal translation, remember that lies to you. So if you see x plus 2, it's really moving to the left. When you see x minus 5, it's really moving to the right. And of course, the vertical translation out back goes the way that it should go, right? So if it says plus 2 out back, we're going up 2. And if it says minus 5, we're going down 5, right? So let's look at example 5 and talk about what transformations are there. We'll graph the original function, and then we'll graph the transformed function. So we have a vertical dilation by a factor of 3. And that's because of the A value, right? So again, a vertical dilation by a factor of 3. We have a horizontal translation. Which direction? It's plus 1, right? So again, the x lies to you, so it's not going to be to the right, it's going to be to the left. So this is going to be a horizontal translation left 1 unit. And a vertical translation where? The minus 2. So it's going to take us down 2 units. Okay? So what is our base function? Again, get rid of all transformations, just think about the base function. Our base function is log base 1/2 of x. And so converting that, that's going to be 1/2 y is equal to x. So I'll get my table of x's and y's. And so when y is 0, x is 1. When y is 1, x is a half. When y is 2, x will be a fourth. When y is negative 1, we get 2. And when y is negative 2, we're going to get 4. And so my original points, right? So we're going to plot this in red here. My original points, 1, 0, 1 half for x and 1 for y, a quarter and 2. We're looking at 2, negative 1, and 4, negative 2. And so those 5 points would be just the base function, log base 1/2 of x. But I've got to multiply all these by 3. I got to move them left 1 and down 2. And so what I like to do, and this is my method, it makes sense in my head, and I show this because for some of you it'll make sense as well, right? And remember, order of operations still apply, right? So the vertical dilution says I have to multiply the y values by 3, right? So I'm going to times this by 3, times by 3, times by 3, times by 3, times by 3. And when I do that, I get 0, 3, 6, negative 3, and negative 6, right? So those are my new y values, right? Because this would be 3y. Okay. I'm going to stay with the vertical for a second. Now it says I have to shift them where? Down 2. So now I need to take all those values and do 3y minus 2. And so when I do that, I'm going to end up with this. So I'm going to put negative 2, 1, 4, negative 5, and negative 8. Okay, so again, my final y values will be this column here. Now, what do the x's need to do? They all need to move to the left 1. And so my x's, I'm going to end up with x minus 1. And so 0, this will be negative 1/2, this will be negative 3/4, this would be 1, and this would be 3. And so my final ordered pairs, the ordered pairs for this function that I'm going to graph, is going to be the green column and the orange column. Those are going to be the ordered pairs for 3 log base 1/2 of the x plus the 1 minus the 2. All right, and so again, my ordered pairs will be 0, negative 2, negative 1/2, 1, negative 3/4, 4, 1, negative 5, and 3, negative 8. Those are my 5 ordered pairs that I'm going to graph. And so putting those on the coordinate plane, 0, negative 2 is here, negative 1/2 and 1, negative 1/2 and 1, 1's up here, negative 3/4 and 4, 1, negative 5, and 3, negative 8. Now, our asymptote would be at x equals negative 1, right? Our asymptote got shifted to the left 1 as well, and so our asymptote's at x equals negative 1. And so this is going to be very vertical here and then coming down, stretched out like this. So again, this is not going to cross negative 1 for x. Okay, so there's our transformations. And again, if you think about each piece, if you think about what it does to the function, and remember order of operations, which ones have to come first, multiplication first, then addition and subtraction can deal with later, we can see how this table builds out, okay? All right, last example, example 6, finding inverse of exponential functions. At Earth's surface, the air pressure is defined as 1 atmosphere. Pressure decreases by about 20% for each mile of altitude, and the atmospheric pressure can be modeled by P is equal to 0.8 to the x power, where x measures the altitude in miles. And so we want to find the atmospheric pressure in atmospheres at an altitude of 12 miles. Well, if P is equal to 0.8 to the x, and the x being 12, so then we would get that P is equal to 0.68, sorry, not 0.6, 0.0687, and so that is in atmospheres. And so basically you could think of this as like a percent. So the atmosphere is only about 6.9% as thick as it is at the Earth's surface, right? Because again, if we have 100% atmosphere at the surface, that being represented by the 1, we're down to about 6.9% of the atmosphere at 12 miles. Hence why you need oxygen when you go that high. All right, so write the equation for the inverse function. And so we're going to take this function here and write its inverse. And so what we're going to get is, remember that p is equal to 0.8 to the x. And so remember what goes where in a log, so we get the log. The base is still the base, right? So 0.8 will be the base of the log. And then the p will be what we're taking the log of. And remember, the power is what the log is equal to. And so we get log base 0.8 to the p is equal to x. And so that's it for today. Your assignment is in Google Classroom. Make sure you get it submitted. I hope y'all have a great day. And the word of the day is logarithm. Again, the word of the day is logarithm. So y'all have a great one.